Hello, everyone. Today's walkthrough is going to be a little bit longer. I was thinking of splitting this into two different segments. We had that. So this is technically this is the Wednesday stuff and Monday stuff. There's no clean place to do this, so we're going to do this one's just going to be a big one. It counts for two lessons. But I want to get through the t-test sort of all in one bundle. There's a side step that we have to do. Actually, a couple of them. One I'm going to be doing within the context of a t-test, something about confidence intervals. And there's something that I just sort of pulled out as optional material, the degrees of freedom discussion, which there's two ways of handling it. One is I'll just tell you how to solve it, which is a very simple thing, which requires no time. And then the bigger question of what the hell is this is something that a lot of people have trouble with. If you're interested in it, great. There'll be a little short video with it. If not, that's also perfectly fine. I'll talk more about the fact that a lot of people who use them quite effectively and just do it have no clue what they really are. And I was surprised at that myself because I had a professor who explained it in a pretty decent way. I'm going to try to replicate my training on that. So that's an optional thing for people. This is going to be focusing on the t-test. Now, truthfully, there are 4 versions of the t-test. One is sort of the same test. It's just there are 2 versions of it, and I'll just show you one of the 2, and I'll explain what the other one is in case you're interested. But we're just going to focus on the one. So there's really 3 t-tests for our purpose that we're going to be having. Now, this is going to be the same issue we have with correlations, and that is you have to choose, even if you understand that you're doing analysis and it is the t-test. I'm sorry, I don't even have the screen up correct yet. There we go. Even if you don't have the, or you know it's a t-test, doesn't necessarily mean that you have that you know what the right one is. I mean, there are 3 to choose from. So part of what today is about is making sure you understand the distinction between the 3. It's really, in terms of, if you can get to the t-test, you're pretty much there. Deciding between them is not nearly as difficult a decision as it might sound. And I'll explain why and what to look for in these cases. Now, these pictures down here, I will at least mention this because you're going to find out that whenever weird stuff happens in my life, it means I've usually lost a bet. And when I lose a bet and I have to do something in the classroom, I always put it in stats for no reason. So I have a friend who loves puns, and I lost a bet, and so now I have to do some pun related humor. So look down the pictures down here. It's a t-test. He's testing the t. Isn't that hilarious? If you like puns, you may find that funny. If you hate puns, you understand that I'm doing this because it's a matter of honor that I do this. The second one, if this first one is a t-test, what is this one? You are correct. It is a tree test. Puns are the lowest form of humor, aren't they? And this one, I had a student just send it to me because she thought this was me. So some time has elapsed. I'm a little bit both whiter in the beard and chunkier in size. But she thought this was me, and I thought, yeah, that's sort of what I do, is get dressed up and go to tea parties. But she went to the effort of doing this. So these first 2 were because I lost the bet. The second one is to show you that some people actually do enjoy my company and the way that I do things. So, whatever, haters. Okay, so we have some t-tests to do today, and we'll start by talking about a specific thing, and then we'll sort of circle back to what a t-test is. The shorthand version is this is one of the first, and we'll find out one of the sort of mainstays of analysis when we're doing psychological research is a t-test. The t-test is, as I sort of mentioned in the last video, it is a simplified version of the analysis of variance. So this is a shortcut. And even today, one of the t-tests we have, there's a shortcut of a shortcut to use. And that's the one where there were 2 versions and we're using one of them. The idea of a t-test is we have essentially 2 groups. It's That's correct, but the groups themselves are a little bit different than we've been dealing with in some cases. So we have 2 points of comparison, either 2 groups or some version of 2 things that we're going to be comparing. And the test is developed in such a way that it's going to measure things in these states of 2. And the research question or the statistical question of this is, are these 2 groups separate enough? Remember in the last video, I made that point of really what we're looking for is separateness in the group mean. So if these are distribution, we start them off, so group A, group B, only 2 groups in this case, so group A and B, they get different manipulations during the research project. And the idea is that over time, the curves shift. So between where they started at originally or theoretically, and at the end of testing or after we have introduced our manipulation, you expect that some change has happened. And these represent the curve of data. Okay, so this would be a curve that has very little variance, so just a tiny high curve. This would be sort of a curve with a lot of variance. So this is just a curve with sort of like normal variance. This would be like 2 normal distributions, one for group A, their result, and one for group B for their results. After our manipulation, although they started alike, we expect our manipulation to have worked, and there will be some separateness of them. Okay, if there is a mathematical difference, one that we can sort of say did not happen by chance, we expect this distance between them to be what we consider, as you saw last time, statistically significant. The t-test is designed to make that measure when we have a 2-group situation, right? So it's just, it follows everything we talked about last time. This is just for when we have 2 groups, okay? The analysis of variance is when we have 3 groups or more. They're doing the same thing, okay? Looking for that separateness between groups. Now, when we talk about the analysis of variance, I'm just going to mention this up front. The idea is that there's extra variance that a 2-group does. So if you have just a 2-group thing, you have this group versus this group, and that's really the only difference you're looking at is between these 2 groups. If there's a 3rd group, and I don't really have a 3rd hand, so there's my elbow, group 1, group 2, group 3. I have if I'm making comparisons, I have group 1 versus group 2. Oh, this is going to be weird. Group 1 versus group 3, and a comparison between group 2 and group 3. Okay, so I have extra comparisons I'd have to make. And having an extra group in there means that there is more variance, more error that is possibly going to creep in. So we have to analyze things differently. We have to take in that extra source of variance and now combinations of different pairings that we could do, different kinds of 2-group comparisons that could be made. So this t-test is just the pared down version for when we only have 2 groups. So it doesn't have certain variances that the analysis of variance will. This is that simplified version. Okay, so what we're learning today, that the thinking behind it between this and the analysis of variance, exactly the same. The difference is that the analysis of variance is when we have more sources of variance. And in a t-test, we have a lot less variance. We have one entire source that doesn't exist, which again, we'll talk about with the analysis of variance. So this is that special pared down version, okay? But what we learned about the t-test also applies to the analysis of variance, right? Just as I said, all parametric tests share these qualities, these assumptions of the analysis. So they're nominal, they're not nominal, not ordinal. They have to be interval or ratio data. We assume that there's a normal curve, so error is distributed evenly. We assume that the scores are normal and representative, and so on. So the idea is that even though we're learning some things about the t-test, the same stuff is going to apply to the analysis of variance. So I won't be double dipping and recovering things, some of the things when we get to that analysis of variance. Okay, so 2 groups, one versus another. Now, with the t-test, we also have this little oddity that pops up. So we're just going to deal with it first. In the end, you're going to find out, I'm just going to say, do it this way. Okay, when you're learning how to do research, you don't worry about some things. You know, we want you to learn how to do it. You have to sort of learn how to ride a bike before you enter your first biking marathon. So we're learning the rules, and there are exceptions to these rules, but you're not at the level where exceptions are going to be creeping in. So you need to know this, but in a practical sense, you're just going to be doing it the way that it's done and not worrying about the exceptions. Okay, but you're going to run across these terms and you're going to run across them in some of the things we're doing. So I have to at least explain what it is. Otherwise, it will be confusing when you just see these terms being thrown around. So the first of these is going to be something called the one-tailed test versus the two-tailed. Now, you've certainly seen this graph before, and all the way through so far, and really kind of all the way through in reality for us, we have been talking about and we are going to be doing something known as a two-tailed test. Okay, the one-tailed test is sort of the exception. And if we go back to the normal curve, I don't have all the lines in this one. I just sort of cut and paste from another, from last week's PowerPoint. We have sort of here, and this is supposed to be the positive and negative 1.96 z-score. That means that at this end of the curve, there's 2.5% chance of making an error. And at this end of the curve, there's a 2.5% chance of making an error. So that's that 5% alpha level that we dealt with last time. The middle of the curve is the common area of the curve. And what that means is if the distance between your two data points sort of falls in this part of the curve, the common area, that means that there is no statistical significance. They're not far apart. So the group started off like this. Mathematically, they end up like this. Okay, and they're not really far enough apart. Not quite there yet, but we're getting closer. Not quite there yet. Bam, now they're over that 1.96 line into the rare part of the curve. So at some point there'll be a metric, a measure, which we'll learn is going to be something called the critical value, that if your calculated value exceeds that, it means it's in this rare part of the curve. Now remember, the rare part of the curve, that 2.5% carved off at each end, is sort of 2.5 or 1.96 truthfully, but beyond that is such a small chance of that happening just by chance. It just doesn't occur naturally. We're accepting 5% because we have that 2.5% chance above and below as our alpha level, but things don't end up as outliers, which is really what they are in some ways, by chance very often. They do, it's by whatever risk factor, so we have a 5% chance of that happening. But the idea is that if something is that far out, we're pretty confident it's because of what we did. They didn't start off differently, they ended differently. And we're pretty positive that the distance that they've changed, that distance between the groups is going to be something that was caused by our manipulation. Okay, so what a two-tailed test says, and I sort of mentioned this in the last video as well, just to remind you, there's a reason why I cover things in videos. The idea is that it kind of matters to us. So let's say we're doing something with therapy, and I have a project where I'm introducing a new kind of therapy that I hope is going to make people less depressed, some kind of training session to lower depression. So we measure how depressed they are, and we hope their scores go down. Okay. So what a two-tailed test says is, boiled down, I care if the scores go down. That's what I'm hoping for. That's what I'm sort of expecting in my mind, that that's what's going to happen. But I also have to care about the fact if I make them more depressed by accident. If their depression increases substantially, I kind of want to know that as well. So what the two-tailed test is doing is saying, so if you wanted the groups to go like this, but instead the groups went like this, that's also important. A group that got the good therapy made them more depressed is something I'm kind of concerned about. So it's not just testing what I want to test. I have to make sure that it doesn't go wrong in the opposite direction. So two-tailed means I'm going to look in both directions. If it decreases significantly, in this case with depression, that's what I was hoping for, I want to know that, and then I would use that therapy with my patients. But if I also increase depression significantly, I want to know that, so I know don't ever do this with my clients, and just throw this out and warn people this is a bad thing to do. So I care about change in both directions. Remember when we talked about kurtosis and skew, we talked about, actually more with skew, the idea of skew was we had those tail ends of the curve, either positive or negative skew of a curve. And we just said the endpoints of that curve, the point where it flattens out, are the tails. So what a two-tailed test is, I'm going to look at both ends of the curve. Extremes in either direction is important. One's important in a good way, one's important in a bad way, but I'm going to check on both of them. A one-tailed test says, I have a 5% chance of making the error. I'm just going to put all 5% in one direction. I only care if they if their depression score stops. I'm not even going to look at the other side. So mathematically, what I'm going to do is I'm going to take that 2.5% at the bottom, or at the top end of the curve in this case, and throw all 5% down at the bottom. So if you look at the screen, what that would mean, there's a cursor, instead of having it here, which is, again, this is 2.5%, at 5% of the curve, it may move back to here. Okay, where this little line is. And that's not really accurate, but here's an identifiable feature. So we're going to say that everything past this point is 5% of the scores in this curve. So what I'm saying is I'm looking for direction, or I'm looking for change only in one direction. Now, that may be appropriate, but really statistically what's going to be happening is you are making it more likely to find a mistake if it occurs in one direction, and you're making it impossible to find a change in the other direction. But that's what a one-tailed test does. And sometimes when people use a one-tailed test, it is because this is the only direction that matters. It really doesn't matter if it goes in the other way. But what we're going to find out, and you'll understand this a little bit more when we start talking about the critical values a bit, you're actually making it easier to find a difference in that fashion. We'll see the critical value that the level that you have to sort of overcome to say this is statistically significant changes, and it's easier now. So the value you have to overcome becomes lower if you put everything off to one end. So a one-tailed test is what we would consider a predictive outcome. That's what you're testing for. If it only matters if scores go in one way, you can justify doing a one-tailed t-test. Our standard is there are very few things where you would ignore changes in the other direction. So two-tailed test says we're checking both ends of the curve. Improvement or decrease is going to matter for us. Okay, so that's what this is all about, and that's what one and two-tailed tests mean. Now, whenever, and this is just some of that, I just didn't go ahead to the next slide, but you have, thankfully I use a similar example to this. When we're doing a test, remember there are always three potential outcomes. It could be that the mean that we obtain, which is our group, is greater than the mean we expected. Okay, so our statistic would be statistically significant. In a positive way, scores increase. It could mean that the mean that we obtained is less than the mean expected. And again, if it's significant, it means it overcomes a critical value. We care about if scores decrease as well, or there is no difference. What we're going to find, if you think back to that null hypothesis, which was there is no difference, and we hope to reject that, if the scores are enough in the positive direction or the negative direction, scores increase or decrease. If it's above that critical value, we can then reject the null hypothesis. Now, you've heard me talk about this. The last one, by the way, was a little bit more rambly than I meant it to be. I apologize. I sometimes go back and listen, and I looked at that one. I thought, crap, that went a little bit off a little bit more than I wanted it to, about some extra stuff you probably didn't need to know about. But the idea here is when we put this into practice, even if it's confusing right now, it'll snap into place really quickly when we work through an example. So if it's still not there, it will be soon. And you'll see that the actual choices you make are pretty straightforward of how to do it. However, if we go through these sort of simple things, or things I'm referring to as simple, and it doesn't make sense, please go ahead and let me know. And I will either deal with you individually, or if enough of you have a problem with something, I will throw an email out to the class trying to explain something. I don't think I need to necessarily do another video, but if that was necessary, I would do that as well. This is part of the being away, sort of, I can't be there to answer immediate questions in the classroom. Okay, so those are the rules. Certainly read through this, but the next slide, I sort of say the decision rules. And the first one is do the two-tailed test because I say so. That's our default, just like alpha 0.05. Yeah, you can have alpha at other levels, but you're not at the place where that's a decision that you should be even thinking about. Okay, it's really in extreme cases or unusual disciplines and unusual questions that these things come up. The standard is, alpha at a 0.05. The standard is for t-tests. We're always going to be using a two-tailed test. So two-tailed test, alpha 0.05, really set in concrete for everybody. Now, the other two things there are things for you to know about. The reasons why you can do a one-tailed test, so B here is a reason people use. I think C is sort of the compromise position. There are mathematical ways of doing it that you care more about one direction, but you leave a little bit of error over on the other side in case there's an extreme reaction. So I'm checking both, but I'm hedging my bets. It should go in this direction. Yeah, sure, you can use, and this is something called, so the Leventhal and Wynn, it's pronounced Wynn, this sort of lopsided t-test value. You can do that, but you're gonna have to justify it, and there's really almost no justification for anybody at your level. So just do the two-tailed test because I say so. If for no other reason, just that's one you're just gonna give me and do it this way. Okay, so oh, here's Monkey Butler. So he's back again. And the idea is here are the three kinds of t-tests we are going to have. Now, the first one is the purist. It's not the one, we're not gonna do these in this particular order, but here are the three options we have. So I said that we have, the t-test is used to compare scores of two groups. So this is only allowable when we have two different experimental groups, group A and group B. Okay, that's the only option, is that we have these two groups. Now, so you can't have a group C as well. And if you have a group A and a group B and a group C, yeah, you can do multiple t-tests, but as I mentioned in the last video, that increases the amount of experiment-wise error, and that's a problem. So if you have three groups or more, we just default to the analysis of variance. T-test is only for two group situations. Now, the difference between what those two groups are varies a little bit. So the first one is the one that would leap to mind. When I say there's two groups, the first one is what you expect. Is there are two experimental groups. Group A does something, group B does something. I'm going to see if there's a change in their behavior. Okay. So we're going to find out that that's sort of the standard way that most people use t-tests. So that's why it's listed first, although we're going to learn about another one before that. The second option is that we have two groups, but it's really one group of people tested twice. Now, we do this in psychology. We measure rate of change, learning. There are ways that this is done. If you only have sort of a pre-test and post-test, this is the most common one for psychology when there's just two groups. It's almost always a pre-test, post-test design. I have one group of people and I test them at time A and test them at time B. It is the same group of people just tested twice. So it's not two independent groups of people, okay, a between group project. It's a within group project, one group tested two times. So instead of group A and group B, it's group A here and group A here. And I'm measuring the change within this group, okay? Now, because I'm measuring that same group of people tested twice, if I count their variance, I'm just, again, sort of loading this up, priming you for when we get to this later. Because there's really only one group of independent people, if I count their variance, the error that's within this group, if I count it at time one, they're still the same group of people at time two. And what that means is they don't have as much variance as it would be if I had two separate groups. Okay, so where there's one group tested twice, there's less overall variance because they're not independent groups of people, right? So two groups, A has its own group of smart people and dumb people, and B has an entire different group of smart people and dumb people. The distribution of smart to dumb in each of these groups is different. So I have to account for the variation of this group and the variation of this group. If there's just one group, I account for the sort of proportion of smart to dumb once. I don't have to do it again. Otherwise, I'm sort of double counting. And that's a mistake. So we'll find out when we do this, we actually have less overall variance, and a kind of variance is missing when we have this kind of setup. If it's a typical learning design in psychology, we tend to have like 7 days that we test them. Okay, if we're doing animals, it's like for an entire week or an entire 3-week period, whatever you're doing. So if you have more than two times of testing, you go to the analysis of variance. But if you only have this pre-test, post-test, there's a t-test that's designed for this. This is called either the dependent group or the correlated group t-test. And the last one is the one that I had to sort of hedge the bet saying that when I talked about two groups, this one was the one that's a little bit more harder to conceptualize until you think about it for a moment. In this group, I have one group of participants. And so here's group A. And I'm comparing them against not another group of people that I'm testing. I'm comparing them to some larger group that has already been tested elsewhere. So this would be, I'm comparing performance of my students versus, or my participants or my athletes or my team versus the average of all of those sports players across the country. Or if I have something like it's an in-classroom kind of thing, here's how my kids did on a test, here's the national average. So I'm comparing one group of people against sort of a national norm, some score that is known at the population level. Now, when we do this, this is a t-test where I have to give you information. I have to tell you what that second group is, what that value is. And you're comparing your one group of people against that normed group of individuals. So there's only one group of people you have, but there's variance in this normative group, or this national size group, population size group that you're comparing it to. So those are the three options. And you can see that this is pretty simple to determine if, you know, which of these tests is going to be. You'll see it when we look at the data. The first one we're going to do is the last one there, one score, a single t-test, one score against a national norm. The biggest clue you're going to have is there's only one column of data. That's a pretty big clue that this is the single sample t-test, because there's not two groups. Okay, easy to identify. The other versions have two sets of scores, an A and a B. But one is two independent groups of people, in which case you have the first option. One is a pre-post test, which means you take the second option. So it's easy to get through it, but you have to read the questions now. That's becoming more important as we head into this next section, is you really need to get those details out of the write-up at the beginning of these, and that will give you the clues if the data itself doesn't. Okay, so here's our t-test for a one sample mean. Allow me to caffeine up for this. Okay, also at this point, I forgot to say this, you shouldn't need to be reminded of this. You are going to need to work through this. And again, I want you to work through these, both this and the lab day. It is looking like a portion of the class is working through it when we do the work in class. I can see the people watching the videos, but the lab day isn't having as many people watch it. So you're not working through that second set of problems. Let me just say that may affect your homework, and it may affect exam if you're not getting as much practice as possible. These are there, the lab is there for you to practice with. And I do encourage you strongly to sort of do that. I can't sort of make you do it if I was there on campus. And I always hated the idea of just putting people in a room to do math. So there would have been some honor system with this anyway. But I encourage you to work through the lab problems as well. There's only a small segment of people who don't seem to be doing it, and it just sort of dropped off. So whatever, I won't make judgments about that, but work through as many problems as you can. So we need the data sets for the t-test. So there would be 3 of them that is online. It's listed under the classroom data sets, and the 3 more for the lab data set, because that will also be coming up soon. You also need to download, and this is what I should have warned you about. So if you haven't done this, pause the video, go back and download this page. Although to get through today, I'll have some things up on the screen that you can look at, but you're going to need to download the critical value table for the t-test. And again, for this, I put the picture in here so you can go through it, but I want you to get used to sort of looking at the table and reading the table. So if you don't have it right now, that's fine. Just go ahead and you'll be okay. But for the lab, make sure that you have the critical value table out as well, because I won't be showing that. I will just sort of show the answers to this. Okay. So here is a setup. So this is a version of the t-test. Again, a t-test for a one sample mean. We only have one sample. This is the easiest of all the statistics to sort of, excuse me, to identify, because there is only one column of data. This one is just like, if this is what it looks like, you know what you should be doing automatically. Now the setup, it's not really that, not that complex. Let's just put it that way. I threw something together. In this example, we have our class taking a geography quiz, and we have a comparison group of high school seniors across the country. And in this case, the teacher would be doing this because they want to see, is my group of children or my students performing on par with the national average. And this is always by the way, if you go into teaching, get used, this is where the SOL score comparisons are all coming from. So if you're heading into education at either the undergraduate or postgraduate level, get used to this. This is something you'll be doing quite a bit of. Okay, so notice that if this was the setup of the question would start here, some description of what's going on, what the X scores are. So this is their raw score out of 70 on this. And you first look at your class, you're like, well, that's not great. I don't see a lot. There's, one who's in the 60s, but everyone else is below that. I see no 70. Should I be worried? Well, we do have to also figure out what the national average is. And that's not presented here, but it would be presented in the question itself. If this was a direct question, and I'll just put it in later. I didn't want to throw up an extra number in there to confuse you yet. I'll show you where you put it into the formula as it goes. So this is just the raw score, but we do know this test is out of 70. So your students are above 50%, most of them, but you can't really say much more than that at this point. Okay, so again, have your formula pages out as well. The formulas are going to be up here, and I'm not going to waste a lot of time on this. By now, you should know how to get the standard deviation, okay? You need to know how to do this. I'm not going to be laboring this particular step. So sum of squares, then do the standard deviation from that. So we'll rush through those portions a little bit quicker. I do want to make one note, and so exam 2s should be arriving to me tonight. Okay, there was a mix up between me and Sammy. So truthfully, what I'm going to be getting hopefully tonight is homework 3, homework 4, and exam 2. So they're all coming in one big group. I'll be grading these as quickly as possible. But what I did notice on exam 1, which was those people who are using sort of the old-fashioned version of standard deviation, which is doing the individual deviations and then going through a different process, not using the raw score method, which is what I've showed you. Those people did have a lot more arithmetic mistakes show up, and they lost a lot of points on questions I really understood they knew the answers to. So I am encouraging once again that if you are doing it the way where there's a lot of, you calculate the group mean, subtract the group mean from every piece of data, you're going to end up with decimal points and also that's where errors come from. So if you are using that method, please try to switch to this one because as we go forward, some of the steps of the sum of squares is necessary for the formula, but it's also necessary for standard deviation. So don't work twice and don't do the extra heavy lifting of having uneven values and decimal points which end up with a lot of mistakes in them. So that's the last plea I'm going to give you. I can say from evidence, if your score went down on exam 1, you probably messed up the standard deviation, and it was just math mistakes that did it. It was simple addition, subtraction when you were doing standard deviation in that other way. So I promise, I'm probably going to break that promise, but that's the last time I'm going. After I grade exam 2, I may continue to make this known to you guys. But if you're using that old formula, please stop. Use the one that I tried to teach you. It will save you time in the long run. It is easier in the long run and less mistakes in the long run. Okay, so standard deviation. So as always, look at our formulas. You should, if any formula is being rehearsed enough times and done enough times, this should start to sound familiar and you should be able to write it without looking. It should be the sum of squares and standard deviation formula. Sum of squares is equal to the sum of the x squares minus quantity sum of x squared over n. So that means we're going to have to get an x squared column. We're going to have to sum the x column itself, and we're going to have to get n. So this was done for you. I did the summing at least. The sum of the x column is 648. The sum of the x squared column, again, I apologize sometimes when you're doing tables in PowerPoint, the subscript, superscript thing doesn't work when you put them into these tables. And it's a pain in the ass to go back and do it. So sometimes it says x2. It's supposed to be x squared. Okay, I know. You don't need to tell me it's a typo. I know it's a typo. That one is one that I know about and actually am just ignoring. Okay, so x squared. Sum of the x squared column is 27,790. Take those things, plug that into the sum of squares and solve. So I will pause for you to do that. And by the way, that meant you should have paused the video and then come back when you're ready, in case that wasn't clear. Okay, so let's go ahead and see what we get. We get the sum of squares equal to 1546. So make sure that that's the value you have before going forward. On the lab work, I'm leaving these columns for you to do. Okay, so please do them, because this is where, again, most mistakes are coming from, is in the simple beginning parts, but those mistakes carry through the entire problem. Okay, so we have our sum of squares 1546. To get to the standard deviation, lowercase s, is equal to the square root of quantity, sum of squares divided by n minus 1. Now, today, when we start talking about degrees of freedom, I am going to be talking about these -1 thing. Actually, this is in the optional lecture, explaining where those -1s come from in the degrees of freedom portion. For us, remember that our formulas, because we're working at the sample level and we're going to be estimating essentially to the population from which it comes, this allows us some of the error in estimation. We can't predict exactly what the population score would be. So we're going to create a range of scores and say the population scores falls into this value. This will be done directly today, and with this problem is something known as the confidence interval. So I want to warn you that that's coming up with this one-tailed t-test as well. So there's two things we're going to be doing with this t-test, but I'll try to explain where those -1s come from. Also, I said this earlier, but just to refresh your mind, if you go into a sociology class, they work at the population level rather than the sample level that we do. Their formulas, if they're calculating on the population level, they will not have these -1s in their formula. So if you end up working in another area of social science, if the formulas look different, it's check to make sure it's not this -1 thing. You can certainly understand that if that is different, your answer would be different. So make sure if you're in a sociology class, you're not just blindly using the sample statistics when you should be using the population statistic. And that idea is that these -1s tend to be vacated because they're not estimating, they're testing the population. So be aware of that. Liberal arts, you're going to run into this. A lot of people in psychology do things with the sociology groups, either now or in grad school. Make sure you understand the difference in how we're doing research at the sample level versus what they're doing at the population level. The formulas are the same except for these -1s showing up. Okay, you have been warned. All right, now hopefully you pause me and at some moment in there and solve for this. So plug 1546 into the n-1, solve for standard deviation, and let's see what we get. Okay, you should have received a sample standard deviation of 10.15. Now, again, for this one, there's only one group. We're only going to be figuring out the standard deviation for the entire group. We're not going to be doing like we did in the point by serial correlation, and we won't in some ways. Standard deviation here certainly is only on the one group that we have. That will change when we have two groups, but here, done. Okay, so we're going to pop those into the corner for just a moment. And then we go to step 2 of this. Now, step 2 is a new concept for us. And again, this, you think I'm long-winded, and I acknowledge I sometimes use 1,000 words when tens would do. But the idea is I'm also going to have points where my tens of words or my thousands of words, I could have used millions. And this is going to be one of them where I'm going to go for a shorter version of this. So you may not understand exactly what the standard error of the mean is. For our purposes, this is really the only place it's going to come up as part of what we need to do. So I'm not going to spend a lot of time on this. The standard error of the mean can be figured out for any of, so on the analysis of variance, we can figure it out for almost anything that we've been doing. This is the only part where it shows up in the formula. So the standard error of the mean, okay, is if you sort of look at the formula. So we start with the standard deviation of the group and divide by the square root of n. It's certainly not a difficult calculation to make. What they're trying to get at with this is estimating how much variance is associated with a single score. What is the average variance carried with the individual score? Now, is that an important concept? Actually, it is. But for the way that we're learning stats and the kinds of stats we're learning, it doesn't show up an awful lot. It's a more indirect kind of thing. So I'm not going to spend time on this, but you do need to know what standard error of the mean is, at least in terms of the calculation side. So I at least want to explain what it was. So this would be the overall group has a certain amount of error variance thrown into it. This is essentially, it's not exactly this, it's a close enough explanation for it. It's the average of any one score, how much variance or how much error does one score from this group carry with it. Now, again, if we were doing power, that actually would be something which would be, if we did power analysis by hand, that would be something we would want to, or we'd have to calculate, but we're not. So this is the only place it's going to show up in terms of your formula. Standard error of the mean, the denotation for it is X with a sub X by it. And that just means it's group X. Okay, and since this is the only place we're using it, that's all you need to know. So it's a standard deviation, which we just calculated, divided by the square root of n. Okay, so pause here. You have both of those, so plug the values in and solve. Okay, so pause and then come back in a bit. Okay, so the standard error of the mean, so the standard deviation for the group was 10.15 divided by the square root of 16. When we solve that out, it is equal to 2.54. Now, it is part of the t-test. It is also part of the confidence interval calculation. That's really the main place that we also run into standard error of the mean. And we are going to be doing that, but we're going to be limiting confidence intervals, although we can do it with any of the analyses that we've been doing. We're going to limit confidence intervals to the one sample t-test because we have to calculate standard error of the mean anyways. So when we get there, confidence intervals are something that can be done for any of our statistics, but you require the standard error of the mean to do so. This is the only place we're going to be calculating the standard error of the mean. So this is the only place I'm going to have you guys learn confidence intervals. But please understand, it can be done for any measure that we've been using. Okay, so quick and easy to standard error of the mean 2.54. And again, you'll see in the formula in just a bit where this sort of shows up in the actual calculation. Okay, now we're also adding the new things in. And in this case, one of the things I'm going to ask you to do, at least for a while, is to state the null hypothesis. So the null hypothesis in its most general form is that there is no expected difference, no expected change. And if we have a one sample test where our goal is, here are our students or our writers or our whatever, and we're comparing them to a national average, we have to find a way of saying our group is no different than the national standard. Now you can actually say, for the null hypothesis, you could write it out as, we expect no difference between our students and the national average. Okay, that's one way of writing it, but we can also shorthand it. The value that we actually end up comparing through these statistics is the mean. So our null hypothesis could just be stated, I hope I don't go too far. Okay, X bar, the mean of our group, is equal to 32. So let's talk about 32 for just a second. Note in this, and if this was on homework or on an exam, this information would have been in with the original setup of the question. Okay, I took it out because I wanted to explain it and how it shows up and why we need that information before we get there. Okay, so note for the single sample t-test, the value of mu, and that's going to be this sign right down here in the t-test formula, that is something which will be given to you. It will always have to be part of the setup of the question. Now, we are going to run across mu in other formulas, and in those cases, it may not be listed in the question because those are different analyses. In those cases, you might have to assume something about mu. Okay, so this is why I don't mind giving you the problems. You still have to know certain of the little glitchy things with each of the formulas, and you're going to have to remember those things on exam day. So just be aware. I'm going to help you out every place that I can, but some things you are going to have to remember, the sort of like, this is an exception case, this is what mu means, or this is what this particular test does. Okay. All right, so in this case, the average score of high school seniors across the country, and again, we assume this would have been from the previous year, the average score of students is 32. So we're going to be comparing our group, their mean, against this group of 32. So we assume that our students are like everybody else. The null hypothesis says I don't expect my group to be any different. We're starting with the assumption, with the null hypothesis, this is our class, this is the national mean, that sort of the mean would be right here, the middle of the curve. This would be equal to 32. This is what, if the null hypothesis is true, this is the most direct case where our scores are equal to 32. Okay, if our scores are better, I'm sorry, it's always backwards on screen, sorry. This would be your better, above, and this would be below. Okay, this is the video's mirror image. So if you see an instructor saying above or below, it looks like they're doing the wrong part of the curve. This is mirror image, so just be aware of that. we're going to be comparing, this will be stable, and comparing how our group moves in comparison to this group. And is there enough distance between our group? And again, I'm sort of talking about this as if it's a physical distance, and the physical distance, is the distance between the calculated score of our group and the mean we're comparing it to. But visually, I'm doing it as physical distance, but it's not really physical, it's the mathematical values in there. So this would be given to you in this case. So the null hypothesis could be stated as the mean, and if you want to get specific, the mean of our group is equal to 32. Okay, that would be, if I asked you to do the null hypothesis, that would be as much as is necessary. Now, this will change a little bit if we have two groups. Okay, we'll learn how to write that out when we get there, or three groups and beyond. But this is also, you could write it out, I expect no difference between my students and the national average. That is correct. Or you could just do the mean of my group is equal to 32, which would be that our national average. Okay, so here's a formula for the t-test. T-test is lowercase t. Okay, again, each one has its own symbol. So lowercase t, and also there is a test out there that has a capital T. So getting the lowercase t here is actually important. Okay, just forewarning, we will be doing that other test. So it is important that you make sure you're using the correct lowercase here for this. So lowercase t means it's the t-test. It is equal to the mean obtained. OBT always means obtained. So that is for your group. You'll have to calculate this. We haven't calculated it yet, but it's a simple calculation for us. Minus mu, and that's this little U/W looking thing. This is going to be given to you. Okay, and here for this instance, we know that this is going to be 32 over the standard error of the mean. So S sub x, and that's what we just calculated. So all we have to do is calculate the mean first. So column X, sum of column X divided by the number of participants in column X will give us a mean. So you plug your group mean in here, plug mu in here, plug in standard error of the mean there, and go ahead and solve. So you can pause here, solve for t, and then we'll come back and compare. Okay, so let's plug everything in and see how you did. So we calculate our mean. I think there were 16 in this. I didn't test, but I'm going with it, 16. So 648 divided by 16 minus mu, the national average of 32, over 2.54, which was our calculation, or the calculated value for the standard error of the mean. Now, truthfully, we don't directly use the standard deviation. We're not directly using the sum of squares. In other formulas, those are directly things that go into the formula. Those things are necessary to calculate to get to the standard error of the mean. Okay, it's just a step along the way. And that's why I said you would be calculating these things all semester long. So please make sure you've got the sum of squares, standard deviation calculations down. And you seem to, so that's going to be fine. Now, solving for t, just solve for this formula. 40.5 minus 32 divided by 2.54. Again, I assume that at this point you're able to do that. You should have got an answer of 3.35. Okay, now that is the calculated statistic. Now, up until this point, that's where we ended. We didn't do anything after. Now, truly, it should be t is equal to that. I mean, I did make you put r down for correlation, but there's more. And remember, I said each group, each time we move into a new segment, so after exam 2, you're going to be adding things. Now, we certainly have added in the null hypothesis. That's one thing, but we're now going to be adding in an additional piece. And it's actually a couple additional pieces. They're nothing. They're really not that bad, but you need this for the answer to be complete. Okay, so there's this concept called the degrees of freedom. And these, by the way, the degrees of freedom formulas will be provided for you. If you look at it, you see it's not going to tax you to do this. Now, I just need to mention this. There is sort of a video, or there will be a video. I'm going to do other things first before I get back to it, but hopefully it'll be up very soon, explaining what degrees of freedom are and all the sort of rigmarole behind it. It's not a lot. It's just a weird concept. It just is a weird concept. And it's really simple in practicality. So if you want to learn what the degrees of freedom are, there'll be a little video. If you're going to graduate school, please learn it. Because you will be asked questions about what it is. And it's always something professors do at the graduate level to sort of see who really understands statistics and who doesn't, because it makes it seem like a big thing. But we sometimes ask questions of students that aren't directly on our plate to see how deep their knowledge goes. So I will let you know with psych majors, things like from this class, always being able to explain why correlation does not equal causation is something we do at the undergraduate level and the graduate level. At the graduate level in stats class, they're going to ask you to explain what degrees of freedom are at some point. So it's important that you know this, if not directly, for later. Also, magical number 7 plus or minus 2 is always something psych majors should know. How the damn neuron works is also something you should know. And those questions will be asked. And Jessica and I have killed ourselves probably in intro, in cognition, in sensation perception. Biology has tried it. Chemistry tries it. All of us try to get you to learn how the neuron works. And we're always astonished that even our best majors sometimes are still struggling with it. So please learn the neuron, if nothing else. But these things will show up in the future. So it really isn't just useless knowledge. If you're going forward, this stuff, these are things you should know. And a lot of people don't. And then you have to, you're not at the lead at that point in graduate school. So this is a little leg up. So if you're interested, probably, well, I'm going to say it should be about 15 minutes. Probably for me, it's going to take like 3 hours, but it should be short. I mean, I hope it's going to be short. So look at it if you're interested. Calculation's simple, and these will be provided for you. So for us to go forward, we can just do it. Okay, so degrees of freedom formula is n minus 1. All scores are free to vary. You need to watch the video for that to make sense. But the formula is degrees of freedom minus 1. N is, in this case, is 16. So degrees of freedom for this particular test, 16 minus 1. Our degrees of freedom are 15. So that's the calculation of it. And each of these tests will have a slightly different, in some cases, slightly different formulas for the degrees of freedom. So make sure you're using the correct degrees of freedom formula for a particular analysis. Okay. Now you need this to do some things, and you also need it to go in your final answer. And we're now going to have a format for our final answer. So there is now a correct way to state your final answer. Okay. Those things will, of course, also be provided. Okay, so step 4, here's another new step, something we haven't done before. Now we're going to check for statistical significance. So we know what our group mean is, and if you look at this, we certainly know, going back to our mean 40.5, our class did better than the national average of 32. But the question is it high enough to be in the rare area of the curve where this is a meaningful difference, or is it not far enough ahead? And that means in that common part of the curve. Now, as we've been talking about it, as I was doing the hand thing, distance, keep in mind it's the distance, but it's also the variability within a group. So this is sort of assuming there's a normal curve, and physical distance is a nice image of that. But in practicality, each of these curves also has variability in it, and that's the kurtosis stuff we talked about, the variability of the curve. Skinny flat curves, normal curves, platykurtic curves. So if it's a normal curve, this distance looks great, okay, or looks okay. If it's platykurtic, there's overlap here. The curves aren't far enough apart. So we have to take both of those things into account when we're doing it. It's not just is there enough, is the number bigger or smaller, but in comparison to how variable the curves are, does it overcome a certain specific distance? And again, that's what the critical value tables are going to be. Okay, so I've got one online, so don't worry about it for today. But when you do the lab, and certainly on homework, you're going to need to have that table with you to look up things on the critical value table. Okay, so step 4 is our checking of significance. We have to go to the critical value table, and for the t-test, there's a table for the t-test, a table for the analysis of variance. There is one for correlations. We just didn't worry about it at that point. But for all the other tests, the chi-squares, the Wilcoxon, there are going to be all sorts of other tables. Make sure you have the right table for the particular test and use the right degrees of freedom formula for that. Now, we're going to be looking up in this table what is known as the critical value. That is a value that it's a stated value. So let's say it's 1.7. Okay, we'll learn what it really is with this group in just a second. But let's say it's a value of 1.7. I don't know why my fist is here. I was thinking I was talking in group for a second. So I'll just put that away. So our value is 1.7. What we're going to do is compare the calculated value, the solution to the statistic we just did, compare it to the critical value. Now, for 95% of the statistical tests you're going to learn this semester. The standard way that it is done, and certainly for all the parametric statistics, for everything on exam 3, here is the rule. If your calculated value is equal to or greater than the value that's in the table, so if our calculated value is equal to or bigger than the critical value, then our finding is considered statistically significant, and therefore we can reject the null hypothesis. If our calculated value is less than the critical value, our outcome is not statistically significant, and we cannot reject the null hypothesis. Okay, so we look up a value. If our calculated value, the outcome of the t-test, if that is equal to or larger than that value in the table, it is significant. If it's not larger or equal to, then it is not significant. Okay, now how do we get this value? Well, we need two things, always. We need to know the alpha level. Okay, that's the amount of risk that we're going to associate with this. So if our alpha level was lower, okay, and lower in this case means more stringent. So instead of a 0.05, we would go to like a 0.01. That would mean I would need a higher actual value from the t-test to overcome it. When you look at the table, it'll be obvious. If I'm more relaxed with it and go to a 0.10, 10% chance of risk of making a mistake, the critical value goes lower. So the bar we have to overcome is actually lower. And so it's easier to find something if we sort of make that our alpha level more risky, is the best way to think about it. For you guys, no cake, 0.05. Why? Because I said so. I don't get to pull that out very often, but because I said so. Okay, always going to be 0.05. Second thing you need are degrees of freedom. We've just calculated those to be equal to 15. So we go forward, 0.05, degrees of freedom 15. For the t-test, we also need to know is it a one-tailed test or a two-tailed test? And this is the other, just do it because I said it this way, we're doing a two-tailed test always. Okay, two-tailed test, alpha 0.05, degrees of freedom 15. Oops, and there's just a slide with a line. Okay, so I guess we're going to solve for critical value. We don't really solve. Other things to notice, and the second point I just covered, that if you increase the risk, scores go down. If you lessen the risk, make it tighter, harder to overcome, then the critical value is going to be higher, and you have to overcome a higher limit. The other thing here is also important. When we're doing things in the t-table or the f-table, actually any of them, but the t-table is really the only place you're likely to end up with potentially negative values. We're comparing two groups, so whichever one you put first could end up with a negative value. If the higher group goes first, it's a positive value. If it's a lower value, you're going to end up with a negative when you just solve, because the top of that is my group mean minus whatever mu happens to be. So I can end up with a negative score. When we are comparing things in the t-tables, we are always comparing, and actually any of the tables, we are comparing the absolute value, which is just the number itself in the absence of plus or minus. Plus or minus for these are directional as well. Not as directional as it is with correlations, because that's talking about a relationship issue. Negative values here mean one group, whatever group one is, had a higher or lower score. Okay? So you could have easily just switched the groups and it wouldn't have caused any issue. But you can have negative values on t-tests. When you compare them to the value in the critical table, it's on the basis of the absolute value. So just ignore the positive negative sign always when you go to these tables. Okay, and then it just needs to be equal to or bigger. Okay, so here is a blank one. I'm going to make this easier in just a second, but this is what your typical critical value t-table looks like. So, oh, I'm sorry. Again, on my screen, every time my cursor goes up, I got a little mini screen that pops down. I forget that it doesn't show up on your screen, but if you see me not being able to read things, it's because my screen is occluded. This top line up here is for the two-tailed test. This line down here is for a one-tailed test. So we have an overall level of 0.05. The one-tailed test, the correlate of that is 2.5% here. So, and what we're going to do is we really want to use two-tailed test alpha 0.05. So this is the place we're looking for, which means this column. And these are for all the other things. If I'm doing a one-tailed test with a 5% error rate, I'm going to use these values. If I'm doing a two-tailed test with 0.01 level, here's a column I would use, and I'm going to use these as my critical values. And here are the degrees of freedom that you have. We are always using two-tailed test, always using alpha 0.05. So this column is the only one we're going to be concerned with. So let me just block that out for you. Okay, so ignore all the other values. Those are just for different ways of setting up the experiment, whether it's one-tailed versus two-tailed, more conservative, more liberal with the alpha level, okay? Always two-tailed test, alpha always 0.05. So this is the column on this table we're going to be looking for. All right, our degrees of freedom. We know that we have degrees of freedom equal to 15, n minus 1, 16 minus 1. So 15, cursor back, 15 degrees of freedom. And again, if you had a ruler, we would just go across. That would give us a critical value of 2.131. And again, use a piece of paper if you're that kind of person. But make sure you're in the right column. Here's another simple mistake people make. As they're going across, they look at the wrong column. So make sure it's for a two-tailed alpha 0.05. So our critical value is 2.131. So let's plug that in there. Now, as I said, if our value is greater than that, that means it is statistically significant. As a consequence, we would go ahead and say that that's statistically significant. We would reject the null hypothesis. Okay, so work with me a little bit. We're going to go forward and then come back a little bit. So our value, and this is, ignore the other stuff for just a moment, our calculated value from the t-test was 3.35. That is greater than the critical value of 2.131. This is the hurdle we have to get over for it to be significant. So our finding is significant, okay? Don't worry about the rest of this stuff just yet. I've got it all laid out for you, just coming out. So we're just doing the comparison here. Our calculated value is above 2.131. Therefore, it is a statistically significant finding. Your class did better than the national average. And again, significantly better than the national average. So they outperformed the rest of the students, okay, as an average group. Not every individual person, but as a group, they outperformed the entirety of the group or of the population that we're comparing it to. Okay, so we're going to come back to the rest of those things in just a bit. But before we go there, we're going to go back and do confidence intervals. Now, remember I said this was being done because we have to calculate the standard error of the mean. And to do that, you need, and you need that for the confidence interval. Since this is the only place that that happens in terms of our calculation, I'm going to show you how to do confidence intervals now and explain what they are. But the formulas are different in other formulas, but the concept is the same. Okay, so here's what confidence intervals are. So a reminder that we're always going from our sample. I tested 20 people, and I'm going to take those results and say something about the overall population from which they come. So I have my class of students, my 16 students, and I'm making claims that if they were part of this overall population, my group outperformed that group. Okay, they would make up a population. They're not making up the population from which we're comparing. Okay, that was last year's students. Okay, but it's the norm that we have. Now, when we are making an estimation, and again, this you have to sort of think back a little bit to regression. And remember, I said when we make estimations, when we drew the least squared line, a simple regression line through the plot of original data, I said there's always overestimations and underestimations. And once we draw the mathematical line through that, we can then have a new value and estimate where they're going to be based on that. So we've lessened the error, but there's still some error there. There's always error. There's always mistakes made when we go from sample to population. Okay, always, always, always going to be there. So what I'm saying is, if this is how my class did, and I want to say, here's the population from which they come, all current students, what would they be? What does the current population of students taking this test right now, what do they look like if my students are a representative sample of them? I know they did better than last year's group, but what population do my students come from? Okay. So I'm going to estimate from my sample to the population from which they were pulled. Now, because there's this error of estimation, I don't want to predict a specific score and say their score should be 42.17. I can't get that predictive. I would be wrong. It's the likelihood of the variability within my group equaling the variability of the population is never going to be correct. It's within this group that I tested. So there's going to be some error in estimation. So when we actually do the prediction forward to the population, and that's what confidence intervals are about, what we do statistically is say, I'm going to give you a range of scores. Okay, so here's my group scored 40.5. That was their average score. Okay. If I look at the population from which they come, I'm going to say the population score from which they come falls within a range of scores. I'm not going to say it's a specific score. I'm going to say it's going to fall into a range of scores. And what I'm predicting is that my score, if it's representative, falls somewhere between these two endpoints that I'm calculating. It's not going to be specifically in the middle, but it could be. It might be right next to the lowest point. So I'm generating a range, saying that because there's some error of estimation coming in, the population scores, if you want to estimate what it is, based on my data, here's a range of scores that it's going to fall into. Okay, not the specific score. I really can't know that because there's always variability. So here's a range of scores, and the real population falls somewhere between this. And I'm 95% confident of this. This is kind of where interval means that range, and confidence is whatever alpha level we're assigning. I'm 95% confident that it falls in there. Now, again, a very simple formula. That's why I'm not worried about doing this. So the formula for the confidence interval, there are some things that you need. So you need the mean of your group, the group which I'm predicting from, because that is necessary to account for the variability of the starting point. Plus and minus, so we're going to do both. So there's one for the upper end, one for the lower end. S sub x, which are standard error of the mean, okay, that thing we calculated for the first time today. And that is multiplied by the t critical value. So the value we looked up in the table, that's actually going to become part of this formula. So to sort of frame it, I'm going to have, if it's a range of scores, I'm calculating an endpoint at the upper end and one at the lower end. Okay, so one of them is going to be plus, and one of them is going to be minus. So we just take that formula and solve it with the plus sign in there and the minus score in there. So our obtained mean, 40.5, plus the standard error, multiplied by the t critical value, which we had. So let me put these in here. 2.54 was our standard error of the mean, the critical value from the table. Based on our sample size, degrees of freedom, 16 minus 1 gave us 15, alpha 0.05 for a two-tailed test. That critical value of 2.13 is included in the formula. So 2.13 multiplied by 2.54 added to 40.5, 2.13 multiplied by 2.54, that quantity subtracted from 40.5, that will give you the upper and lower levels of the confidence interval limit, and that is going to be the range of scores in which our sample is expected to fall from, okay? So you can pause, just go ahead and solve it. This is simple arithmetic and multiplication, so it's okay if I just do this one. What we end up with is a lower confidence interval of 35.09, upper level at 45.91. So if our group does represent the population from which it comes, it's a good standardized sample. Predicting from my sample to the population itself, their average score is expected to be somewhere between 35.09 and 45.91. And there's a 95% certainty that it's going to fall within this range. Now, there's still a 5% certainty it falls on either outside this range. We still have that risk factor that's in there. Okay, so that's confidence intervals. It's for that prediction. You need the standard error of the mean to do this. And in this case, the t critical value, or the critical value from whatever analysis you're working on, is generally part of the formula. Okay, so there's confidence intervals. Now back to the t-test. So the 95th percent confidence interval is the range between those two scores. Okay. Okay, so we're going to go into the next test, and on this one, we'll then actually stop, and when you see that formal answer, I'll stop and explain it. Okay, so in this case, our next one is, our next t-test is going to be the t-test for two independent means, or two independent groups. So in this case, we're not comparing to a population. We have a group A and a group B in our project. They're not the same people. This is one group of individuals. This is another group of individuals. something happens to this group, something different happens to this group. So you can read through the setup for this. This is something where we're disrupting sleep and then giving a memory test and comparing not how to our group of studies compare to the average intro psych student across the country. Does the one who is sleep deprived do better than the one who wasn't sleep deprived? Okay, and we'll talk about the null hypothesis and all of that as well. Okay. So here's our data. So we should be on the second data set here. So you should have this. And again, some of this we always start by looking at the formula and then looking to see what I'm going to have to calculate. Now, again, on exam day and sometimes on homework, there might be extra columns there. I just make columns out and that's to make sure that you know what formula you have, or if you mess up a column, there's an extra one if you had to cross something out. Okay, but you can also just use the wrong test, and so don't look just at the number of empty columns. I went to page end for that. Okay. In these examples, I don't. So here's our formula for the t-test, and this is the simplified version of this. Now, what makes this a simplified version, and the version I'm teaching you, is if we have an equal number of people in both group 1 and group 2, or group A and group B if you prefer. If you have an unequal sample size, so group A has more or less than group B, you can't use this formula. There's another formula that's there. Now, it's on the formula sheet, so you would be able to look at it, and by the end of the semester, you should be able to figure it out anyways. The denominator is what's changing most from this, but we have control over this, so I'm going to make sure our examples have equal sample size. There's really no reason to learn both versions, so I'm going with the one that, since we have control over our experiment, unless something goes wrong, this would be the t-test we would have. We would have equal sample size within our two groups. So our t and obtain just shows up randomly. You know, for this, it's there to help you, but it's not necessarily, if obtained is left off, I'm not going to lose my mind. It's not going to be marked off. So obtained, yes or no, up to you guys for there. But for illustrative purposes, I put it in. So t is equal to, and notice there's not an extra thing after t. That's why I want to explain what obtained was. It's just going to be t, whether it's a one sample test, correlated groups, or this independent means test. It uses the same sort of lowercase t to indicate it. Okay, so they don't know what t-test did unless they look at the experiment itself. So lowercase t just means that this test was a t-test. Okay, so t is equal to, and then on top, the mean of group 1 minus the mean of group 2. So obviously we're going to have to calculate means. On the bottom, square root of sum of squares 1 plus sum of squares 2. So we're going to have to figure out the sum of squares for group 1, and we're going to have to figure out the sum of squares for group 2. We don't need to go to standard deviation. We don't need to go even further to standard error of the mean. All we need to do for this is get to sum of squares. Okay, so just the step 1 of what we've been doing, which is why I said learn this as your standard deviation, because formulas are going to be using this. See, I've already violated the I will never say that again. Okay, no. And then on the bottom, n multiplied by n minus 1. Now, if these two groups had a different sample size, you'd have to have something for group 1, n1, and something for group 2, n2, the number in each of those groups. Because they're the same, we can algebraically just turn it into n multiplied by n minus 1. Okay, so this is the formula you use when we have equal subject size in each of our groups. I'm not going to trick you and sort of throw an unequal sample size in there. Okay, so don't, you know, I'm a jerk, I'm not an asshole, truthfully. So this is the one you need to know. Okay, so we need to calculate all of those things. So in order to calculate sum of squares, you're going to have to calculate the squared values for each of the columns and then sum up all 4 of those columns. And you're going to have to figure out the means for each of them and sample size. Okay, what's the sample size for the groups? Okay, do all of that and then come back. So pause, solve for the x column, x1 column, solve for the x2 column, solve for the squares of x1 and the sum, solve for the squares of the x2 and the sum, and the means, and then come back. Okay, let's go forward. And for the means here, 70.16 is our mean for group 1. Our mean of group 2 is 65.333. N of group 1 is equal to 6. N of group 2 is equal to 6, same sample size. So really just need to calculate it once. And now we have to solve for the sum of squares. So this should be what you have written down. If you're just looking at the answers, you are doing it wrong. Please go back and do this. This is not just looking at the answers. This is you doing it because we want to check, are you making mistakes early on? And if so, we want to know about it so we can correct it. Okay, but here are your column totals. You should have gotten 421 for sum of x1. Sum of the x1 squares, 29,591. Sum of x2, 392. And sum of the x2 squares, 25,698. So we're going to plug all of these things into the formula now. Okay, so we have to get sum of squares first, and we need one for group 1 and the sum of squares for group 2. So for group 1, sum of squares, sum of the x squares minus sum of x squared divided by n. 29.591 minus the quantity 421 squared divided by 6. So for group 1, our sum of squares is equal to 50.833. And then we do the same thing for group 2. Okay, so for group 2, sum of squares is equal to sum of the x squares minus sum of x squared over n. 25.698 minus the quantity 392 squared divided by 6 gives us a sum of squares for group 2 of 87.333. Now we have all the values we need, so we're going to plug everything into our t-test, and it is now on top 70.167 minus 65.333. All of that over the square root of 50.833 plus 87.333 divided by the quantity 6 multiplied by 6 minus 1. Okay, so solve for the bottom, so multiply that, add, do the division, take the square root, do the subtraction, divide the top by the bottom, and then that will give you t. Do it. Okay, that's our next step, is solving for t. So you see it does pick up pace as we go through today. Okay, so solving for that, you should have received a t value of 2.25. Okay, if not, go back. Now again, this one I've rounded to 2 values, so if you still have it out at 3, remember that I round up to 2, but I've carried it through to 3 as I'm doing the calculation. So if it's off at that last point, so if you have 2.24, 2.26, that's fine. Okay, that's rounding, and that's acceptable. If you have 2.3 something, or like 7, or oh my God, if you got like purple, you did something wrong along the way. Okay, so hopefully you got a 2.25. If not, again, this is why you need to have the steps written down. If you were correct with all the values, you know that something went wrong at the last step. If you didn't have the correct mean, for example, you know that there's either something wrong with a column total or your division total. Did you count the number of people wrong? Okay, so showing the work allows me and you to figure out where the mistakes were made. Okay, so now we have the answer, t is equal to 2.25. Now we have to do the other bells and whistles for this. All right, so going forward. So null hypothesis, what would the null hypothesis be? Now remember, for our comparison in the last one, it was against that normal or that national mean, which was known. Okay, now in this case, our comparison is between group 1 and group 2. So the easiest way to write this would be using mean scores. The mean of group 1 is equal to the mean of group 2. Okay, that says it. That says there is no difference. Or I could put it into words, also equally correct, just a lot harder, not harder, a lot more wordy to do this. The amount of numbers recalled, or however you phrase that, the recall scores, recalled by people who had a full night of sleep will not be different than those who are sleep deprived. Okay, or null hypothesis, there should be no difference between the mean scores of group 1 versus group 2. All of those are appropriate. Any of those could be there. Simplest is the mean of group 1 would be equal to the mean of group 2. Null hypothesis always states there is no difference. We hope to reject that based on the critical value comparison that we're going to be making. Now, we didn't do the extra bells and whistles with the first one. So from this point forward, including that one sample t-test, you're always going to have to do these steps now. Just like we learned in the first one, you have to interpret it. You have to interpret the findings of these. We're adding 2 bit by bit each time we're doing something. Each time we pass an exam, new stuff that we carry with us going forward is going to be there. Okay, so now we have to look up the critical value. Now for this one, the degrees of formula is different. For this one, the degrees of freedom formula is n minus 2. Okay, now again, for those who watched the video, or the simplified version was, for every source of variance, which is the individual groups, I have to take away 1 degree of freedom. Okay, so that's where the -1 is. I'm taking away what's called a degree of freedom, or I'm taking away 2 degrees of freedom in this case. Group 1 has its own error, and group 2, or group A and group B, both have their own proportion of error variance tied into this. So because I have 2 sources of variance, I have to account for both of those in my estimation. So I'm taking away a degree of freedom for the first group. I'm taking away a degree of freedom for the second group. So that's where the n-2 comes from. We had 12 total participants. Those are 12 independent people. So 12 minus 2 is equal to 10. So our degrees of freedom, as we're looking it up in the table, is going to be equal to 10. Our alpha is equal to 0.05. We would then go to the table and look up the critical value. So if you have your table, pause and look it up. If not, scroll back or video back or look at it and look at our critical value. So if you went back to the table, and I know people hate when I do this, but get back to this table. In this case, I had 10 degrees of freedom and two-tailed test, 0.05 degrees of freedom. I'm sorry, 0.05 alpha level, 10, and that is equal to 2.28. This is where another version of that table would have been handy. I do apologize. Okay, 2.228. So that's the value from the critical value table. Now, does our value that we calculated, is it greater than or less than this? If it is greater than, then it is significant. If it is not greater than, it is not significant. Well, go back one slide. We see that our calculated value was 2.25. And this is why you have to pay attention. 2.25 is greater than 2.228. We rounded up, that would have been to 2.23. So 2.228 is our critical value. Our obtained value is 2.25. That is greater than the critical value. So this is significant. We are going to reject the null hypothesis. Now, again, you see I put in here just is barely greater. But if you remember back to our last lecture, you're pregnant or you're not. It is significant or it is not. So this is significant. It doesn't matter if it just creeps higher than, or if it is like 97.8. Okay, by the way, for these calculated values, you never really get like giant numbers. They're always sort of in, if you have analysis of variance, it can get up into the 20s, but you don't really see these giant values. For t-tests and stuff, it's like 7 and below for most of them. So it's not the best hint because there are ways it could happen, but it's rare that it's going to happen. So these values aren't going to be really, really large values, especially when you see what we're comparing them to in the t-table. Okay, so we are going to reject the null hypothesis. This is a statistically significant difference. And now we're going to go back to the end of that thing we saw in the one sample test. And there was an entire format here. So here is the format. I'll read the format first and I'll point out what each of these things are. So the final answer here. So now at the end of every question, sometimes I will say, sometimes I will ask for the null hypothesis. Sometimes I won't. For the null hypothesis, if I ask for it, state it. If I don't ask for it, don't worry about it. However, every single response now has to be in this particular format. Okay, with the exception of the regression analysis, which the final answer is a formula. So of course it doesn't fit into this. And we didn't cover this with correlation. So the correlation, just the R is equal to positive or negative, whatever is enough. There are critical value tables for that. And what statistically significant means is different for that. So remember we had, when we did that, a judgment of, is it strong, very strong, weak, very weak? That sort of took the place of the steps of this. So for t-test and further, every answer is going to have this specific kind of format. There'll be some changes given what test it is, but we'll all have these components to it. So the final answer, and again, the exams I'm always saying are in the homework, please circle your final answer. This would be the final answer I'm asking you to circle so I can help find it upon the messy pages that you give to me. Okay, so T with 10 degrees of freedom is equal to 2.25, comma, P is less than 0.05. So let's sort of dissect this. The first thing we have here, this lowercase t, that tells us what test we're using. So you're wondering, well, how does somebody know if it's significant? Do you have to say that? Where are all these pieces of information I say coming from? How do you know, again, I think for the most part, what degrees of freedom are, what the sample sizes or all of these extra things. How do we sort of note that? Well, it's in this particular format. You have to identify first what test it is. So because this is a t-test, lowercase t. For the analysis of variance, it's going to be a capital F. And others for the non-parametrics. Chi-square is a cursive X with a square by it. So that tells us what test it is. So for correlation, it's a lowercase r. That tells us, when I look at the results, what statistic you used. And I understand something about what you're doing. Okay, the next thing, it's supposed to be sort of below and smaller, so subscript. In parentheses, 10 here means that there were 10 degrees of freedom. Now, if you know what degrees of freedom are and you know what the formula for degrees of freedom were, you can work backwards from degrees of freedom, which is provided, to sample size. If degrees of freedom is n minus 2 for this one, or in the one sample n minus 1, I could just go from, in this case, 10 plus 2, know that there were 12 individuals who took part in this research. Okay, so I can work back if that's a fact that I need to know. Now, we don't always need to know that, but sometimes it's an important thing you want to know. Okay, so degrees of freedom tells us something about sample size. Now, really, why is that important? Because we know that if you have a smaller sample size, there is a greater chance of higher error rates. Smaller sample size are always more variable, always more chaotic than the larger sample size. So I can look at this in the finding and sort of say, well, I'm going to have less trust about your results. Even though it's significant, I know that there is much more variation, much more error in this because you have a small sample size, which means that any one score, remember way back, any one score, an outlier, can have an effect on the mean. And it's a worse problem if the sample size is small. Okay, so all of these things, you're starting to see that they are building on each other. It's not pointed out often. Okay, so T with 10 degrees of freedom, a t-test with 10 degrees of freedom, is equal to 2.25. That was the calculation, the outcome of the statistical analysis that we did. It is not the critical value, it is the actual calculation. So this is the outcome of the analysis, okay, equal to 2.25, comma, and then we have P is less than 0.05. This is the decision if it is significant or not. If something is significant, which means I've compared this calculated value to the critical value table, and if it's significant, I'm saying that this is greater than. If something is significant, that means it is less than 0.05. The chance of this being a mistake, an error, chance of that happening is less than 0.05. Now, the one chance that this can happen, if you calculated it and your calculated value was the exact same value as the value in the critical value table, this would change to P is equal to 0.05. Okay, but that's, like winning the lottery, lucky. So the idea here is for significant, if you have P is less than 0.05, that indicates it is a significant difference. As you see down here, if it is not significant, we use P is greater than 0.05. The chance probability of this being caused by a mistake is greater than the risk level of 0.05. Okay, and here that risk level is less than 0.05. Okay, I mean, our value came in beyond that 0.05 risk level. Okay, so that's the final answer now. T test with degrees of freedom is equal to calculated value, comma, some statement about significant or not. Okay, that's how every answer ends now. Okay, the third of three is going to be our correlated group. This one people go back and forth on, so I'm going to get you both of them. Correlated groups or dependent groups. I grew up under dependent groups, but again, your your textbook or your graduate school program may use correlated groups. Whatever. For us, especially in psychology, a two-group within design, which is what this is, almost always a pre and post test. That's the way that this would show up. By the way, I don't know if you can hear it. Otto is snoring and my chair is squeaking. So if you hear noises, it can truly be from either source there. Okay, so this is our dependent groups or correlated groups. So correlated t-test or dependent t are the terms that this may be referred to. So just on this one, just be aware that that's out there. This is closest to the idea of a within group project. We have one group of people, in this case, only tested twice. So time A and time B. If it goes beyond 2 times, we go ahead and use the analysis of variance. what we're looking at with any within design is a change within a group's behavior over time itself. So is there improvement? Is there deficit? Did they learn? It's more about the process of learning rather than differences of the manipulation directly. Okay, we're inferring that with us individual groups. We're looking at that process with the within groups. And for this one, we're gonna find out the different scores come back in. Now there's stuff down here about match samples. Again, that's one of those random, rare things that can come up. We don't tend to find this a lot, so just read it over, look at it in the textbook, but it's not something we're gonna be doing, so don't worry about it for our purposes. And with this particular design, by default, we have to have a person provide both scores, or we can't use them in the analysis, okay? So what we're gonna end up doing, of course, is looking, I've already said it, but there's gonna be a different score calculation. Remember, different score is x minus y, or time 1 subtract from it time 2. Okay, so again, we're gonna put the formula up, look to see what we would have. So that's how you would know what columns you have to do, or just remember these facts about the this particular version of t-test, and it would tell you. So in this one, I didn't have a write-up apparently for this one. We measure a person or a group of people, their depression beforehand. We assume some intervention is happening in between, but everybody is getting the same manipulation. Okay, if it was different manipulations, those would be different groups. So everybody gets the same manipulation, and we're testing them afterward. Did our manipulation cause a change within this particular group's behavior? So the depression score is before and after. I am assuming that if the depression goes down, the score is lower, that means that there is a lower level of depression, but always when there's a write-up, look to see what the scores mean, okay? Because that's important for the interpretation. Okay, so here's our formula. T, and I put the obtains in there again, but on the formula page, you're not always going to see that. So that means you don't need to have obtain there. Just a reminder for us. Our obtained T, our calculated value, is equal to the mean of D. Okay, D stands for a difference column or a difference score. So we're going to have to calculate a difference score and then get the mean of that difference score minus mu. So mu comes up again. And all of this is over the sum of squares for D over n multiplied by n minus 1. So because there's the same number of people, we're taking that same shortcut we did when we learned the independent sample t-test with equal group size. So our n is equal to 10. I've done the columns here. So to get these individual values, we know, so we got to get the mean of D, so we have to sum up the D column. We also need sum of squares, so we're going to need to square the D, or the difference column values, and then sum those up as well. So in terms of the calculations, 10 minus 6 gives us 4, 18 minus 8 gives us 10, all the way down. In this case, you can get negative values, and we count those as negative values. Okay, remember that this is a change. So for this person, even though it's a negative value, since lower scores mean that they went down in their depression. So if a high score and you subtract from the after score, that would typically end in a positive value. If you get a negative value, that means that the score actually went up. Okay, so you end up with a negative value. We got to treat that as a negative value coming through here. So we add up the scores and then subtract the negative values from it. Okay, so that gives us 53. So if you did this, and in this case, we're not doing it with the absolute value, the negative value is part of the mathematical calculation. So our column total is 53 since there are 10 participants. Our mean score is 5.30. That's the mean of D. Square those different scores to get the squared values, and then sum those up, and we get the value of 379 for the sum of the D squared columns. We're going to need that for the sum of squares calculation. So we do the sum of squares calculation. Again, we just did this. So for the walkthrough, at least, I'm going to just go through it. But please do the work and double check me. So pause, even though this answer may be up there, pause and go ahead and do this. Or if it's not up there, go at least pause now and solve for this and see what we have. So the sum of the D's, or sum of squares for D, again, we're using the difference column. We're not using these scores anymore. Remember, when we do a difference column, that's what we're going to be analyzing. So we could have grayed off both the before and after column. This is the column we're working with. So I just changed the sum of squares to reflect that. So I have sum of squares for D is equal to the sum of the D squares minus sum of D squared over N. And notice I took out X's and put D's in. That's because it's a difference column. okay? If you put X in here, but use the values of the difference column, that's fine. It's fine, but I am just being consistent with the columns that we're doing just in case. Okay, but we've done sum of squares already. We've done it 3 times today as well. So 379 minus the quantity 53 squared divided by 10. Your answer should be, dun, dun, dun. Sum of squares for the D column is 98.10. So now we are just going to plug the extra things into this. So we know the mean of D is equal to 5.30. Right there, 53 divided by 10. Sum of squares of D is equal to 98.1. We know N is equal to 10. So 10 multiplied by 10 minus 1. But we have this mu hanging out here. Now, what do we do with this mu? Now, in the one sample t-test, I gave you mu. Okay, I gave that to you as a value. What do we do this time? Well, I'm not going to be giving you a value. This is the first time that you have to remember something about this particular test. For this particular test, the assumption is that mu is equal to 0 because we're doing it from the status of the null hypothesis, because this is the way we're doing it. We expect no difference. So the expected group difference, okay, we take the null hypothesis, I expect no difference. That's really the group we're comparing it to, is 0 difference. So mu for us is 0 always when we do this test. For you guys, it's always going to be 0. Now, the reason I left it in is because if you do things like one-tail tests and the wind felt, there are some cases, and some because of the specific prediction you're making. You are making something a lot more specific. So the choices that you make in the design may cause mu's to be something specific. For your case, it's always going to be equal to 0, but the formula does carry this mu in. So I have to include it because it is part of the formula, but in our instance, mu on this is always going to be equal to 0. And that's just that fact you got to plug in there. And it's something that I can't give you extra assistance on. So for that, mu on this always equal to 0. So we plug that in, 5.30 minus 0 over the square root of 98.1 divided by 10 multiplied by 9. Go ahead and solve for that. So solve the bottom, take the square root, divide that into 5.30, and come back and see what you get for this. And by the way, try to write it in its full final format. Now, I haven't done the degrees of freedom yet, so that's coming in just a second, but that is our goal, is to work towards that final format. Okay, so we're solving for t now. All right, solving for t gives us 5.08. Now, the degrees of freedom, in this case, because there's only one source of variance, one group who's tested twice, n minus 1. So we would go back to that t critical table, and n minus 1 would be degrees of freedom 9. Two-tailed test, alpha 0.05, 9 degrees of freedom, go across. Our t critical value is 2.262. Our calculated value was 5.08, so solving that gave us a 5.08. So the final format for this would be t with 9 degrees of freedom is equal to 5.08, the outcome of our analysis, comma, p is less than 0.05, meaning that it is significant. We reject the null hypothesis. There was a change in this particular group's behavior. Depression did decrease significantly after our intervention. That would sort of be the interpretation of all of that. So I'm just pulling together all those steps that we've been learning. Okay, hopefully you followed through all of that. And again, as I said, it got quicker, but there was a lot of extra stuff in this one. But those are the 3 t-tests. And this is the material start. Actually, the last video started the stuff for exam 3. I will tell you the homework for exam 3 and the exam for exam 3 is the one that oddly seems to take the most time. Even though there's more on the final, this is the one that takes more time because there are just more steps in some of these than in the non-parametrics, which will be on exam 4. So the homeworks are going to take longer now. The exam is going to take longer. So you haven't really been pushing that 3-hour time limit on things going forward. This exam and the final, you might be pressing that 3-hour time limit. So the reason I've also wanted you to sort of, so again, I'm
Yeah. So the other reason I want you to sort of make sure you're doing the work here is that I want you to increase your speed. The more comfortable you are with doing things, the more accurate you are, the more you trust the low-level work, the quicker you'll become, hopefully. And if not, that's something to work on, because it's going to take longer to do the work. If you are too slow and it is taking you too much time, it's going to start causing problems for you. So now we're going to have people like, I wait till the night before and do this and I get it done in time. Let me welcome you to the starting of this is now something that needs to be done probably during lab time, because it is going to take you longer. And this is why at this point, I've warned you as much as I can. If things are coming in late, I've warned you that it's going to take more time. You have the entire lab space available. So if you're using that for something else, that's not an excuse for turning something in late. So I am deducting things from being late now. So just be aware that those deductions are going to start showing up if things are late. If you wait too long to do this, that is now on you, and it's going to show up in the grades from this point forward. And again, another warning, I am canceling classes and labs during the last official week of classes because that last homework is going to take you a very long time. Now, on the final homework, I have seen it take minimum 4 to 5 hours to maximum of 20 hours. And it depends on a whole lot of factors that I have no control over, but you're doing one of everything for that final homework. So I'm giving you the time, but I'm also expecting that thing we've said has been hypothetical all semester. For every hour in class, I'm expecting a certain number of hours outside of class. You're going to need that for that final homework. So make sure you're building this into your workload, that final homework, that last week of class, because it's going to have to be turned in before you guys take off for break, although exams happen after you guys take off, I think is how it's working this time. That due date is going to be before you take off. And I'm going to need to make sure that Sammy can get it to me in time. As a consequence, that's going to be by that Thursday class time. Now, if we were in session, that Thursday class time would still be the due date because we would spend our last class going over the answers. And that will happen this time as well. So again, these are pre-warnings. I'll mention these a number of times, but now is the time I'm going to start giving you these. For the final homework, before you turn it in, please make sure that you have a copy of your responses that you're turning in. I will post the keys for that final homework, and that becomes your study guide for the final exam. Okay, so I will give those warnings, but once it gets turned in, there is no, can you send me a copy of that? The answer is no, they're going to be mailed to me, and I'm going to be grading them once they get here. So I have to wait for them to get here and wait for them to get back. So no, if they're not in on time, if Sammy swoops in, it's counted as 0. So if you wait too long, it's really going to be noticeable. Remember, that final one counts as 2 homeworks because of the amount of time it is going to take. All right, those are the warnings. They're all coming. It has been building, so by doing the work as we go through, hopefully you solve some of those easy problems. Standard deviation should no longer take you any time to do. But if you haven't been doing the work and you have to go back and remember how to do standard deviation, that's extra time. I'm expecting that you know how to do that by this point, and that's something that goes through quickly. Okay, so those are all the pre-warnings for us heading into the rest of the semester. Other than that, I hope things are going well. I hope it is not in the 30s and 40s for temperature as it is up here. And I hope other things are going well as well. All right, thank you.